Well, hello everybody. My name is Muneeba Syed. I'm a research computing facilitator at FAS Research Computing. And welcome to today's new user training class. Today is going to be about introduction to the FASRC clusters. So this is like a very, very general, broad overview. We're going to talk about getting an account. We're going to talk about what exactly high performance computing is and how to use it a little bit specifically in our environment. I'm joined today by two of my colleagues, Paula Sanematsu and Susan Schoenberg. So just to give you an overview of the things that we are going to be talking about today is a little bit about accounts. Some of you may have accounts, maybe all of you, or maybe not. We're going to talk a little bit about how to get an account and how to modify it if you need to make any changes, if you are changing groups or if you're in a rotation, things like that. The next and the main part of today's presentation is going to be about an introduction to HPC. So what exactly is it? How is it different from running on your desktop or your laptop? We're going to talk a lot about cluster architecture and how we set things up here and why that matters, because those are the things that you have to take into account when you want to run a job in order to get your research done. We're also going to talk a little bit about storage, data management, and some general cluster responsibilities that all users have. And the third part is about how do you learn more? Getting started on a HPC or like high performance computing cluster there's a really steep learning curve involved, and it's hard, but there's a lot of payoff. But in order to get there, there's a lot of things that you have to ask, that you got to learn, that you have to figure out what it is that you need to learn. So those might come in a variety of ways, whether it's learning from your lab mates, whether it's looking up things on Google or for your specific software or codes. We have a lot of resources that are available as well. We have our own documentation website. We also have a lot of examples on how to run specific codes on our GitHub. We also have office hours, which is once a week on Zoom, Wednesdays from 12 to 3. And we're also always available via tickets, which is when you send in an email with a question and one of us gets back to you. So starting with accounts, if you already have an account, great. If you have an account and you haven't done anything with it, then these are probably the things that you are going to have to do. One thing to note is that your FASRC account is completely independent of your Harvard Key account or other Harvard accounts that you might have. So if your Harvard email expires or if your Harvard key expires, like if your appointment at the university ends, your RC account is actually completely separate. So if you're going to be continuing your collaboration with your lab or anything of the sort, you can still do that with your RC account. We just might need to update some of the details on it. So because it's a completely separate account, you have a separate username, you have a separate password, and you have a separate two-factor token as well. So those are all the things that you have to keep in mind whenever you're logging into any resources that are owned by us. So if you have a Harvard key, please do use the Harvard key option when you sign up for an account. You're going to set your password, you're going to get your two-factor. We also have a separate VPN. So some of you might be using a Harvard VPN, but that does not give you access to all of the FASRC specific things that we have. So there are some things, like for example, if you're going to be using the Open On Demand, which is like a virtual desktop, if you're going to be working with sensitive data, if you're using any of our licenses for software, if you're mounting storage, those are all things that require the FASRC VPN. So you have to log into our VPN with your RC account. Now, making changes to your account. So many people go through rotations, or they might be doing collaborations with other groups or with other individuals. There are many, many ways in which permissions are very granular, and so it's important to keep those things in mind. So whenever you sign up for an account, you have one sponsor, and for that primary sponsor, you have access to their files, and by default, you have access to submit jobs under them as well. Now, if you're going to be collaborating with a different group, you can request file access through the same tool. It's called Portal. And you say, hi, I'd like to get access to, J Harvard Lab. And the PI or the lab manager, faculty assistant, whoever, they get that automatic request and they log in, they approve it or deny it. But just because you have access to a secondary group's files does not mean that you have access to submit jobs under them. If you need to both access files and submit jobs for a secondary group, you actually need to send us a ticket. You don't need to sign up for a second account just because you're working with other people. one account is all you need and everything that you need, we can work with that. Whether it's if you have to change your email, changing your sponsor, changing your secondary affiliations, all of that. Other things that you need to know is if you have an active account, you will be on our mailing list. On our mailing list, we send out emails that are generally about our monthly maintenances, other downtimes, or other like very important information. And if you try to unsubscribe from it, then your account automatically gets disabled. The other primary way in which accounts get disabled is through inactivity. So, which is accounts that need to be used in the last, it says 12 months, but it should be actually like 6 to 12 months. If you haven't logged in, if you haven't done anything at all with your RC account, then your account is disabled. We don't delete anything. If your lab mates do, that's not on us. But if your account gets disabled and then you need to start using your account again, you don't need to sign up for a second account. Just send us a ticket and we can re-enable it as long as your PI signs off and says, yes, so-and-so is still working with me. All right. Today's meat and potatoes is what is HPC? So HPC stands for high performance computing. HPC is basically the biggest and the fastest like computing machines that we have available right now. And in general, these are going to be like at least 100 times faster than your regular MacBook or Windows laptop that you're probably watching this presentation on right now. So HPC is known by a number of different names, but it all refers to the same thing. Supercomputing, cluster computing, cyber infrastructure, CI, research computing also, which is the name of our department, but this is what we call it. All of these things essentially refer to the exact same thing. So as a comparison for scale, I'm sitting on a MacBook Pro right now, and we'll get into what some of these words exactly mean in a little bit. Let me have a little glossary slide. But on my MacBook Pro, I've got one CPU. And so a CPU is like basically the brain of your computer. And so in the CPU, you're gonna have a bunch of cores. And the cores are what actually do each of the individual instructions anytime you try to do something on your computer, when you open up a browser, when you open up a program, or when you're doing anything at all. So one CPU has 4 to 12 cores, and for the amount of memory that I have available, it's probably going to be anywhere from 16 to 96 gigabytes. So the name of our current iteration of the cluster that we are running, it's called Cannon, which is named for Annie Cannon, who was a pioneer in astrophysics. So when you hear us talk about the Cannon cluster, this is the main cluster that we're referring to. So a typical node, which is like the equivalent of a computer in this case, there's actually going to be 2 CPUs. And each CPU is going to have 24 to 56 cores. And for this one node, there's going to be anywhere from 184 to 2,000 gigabytes of memory. And we have more than 1,400 of these nodes. So that's kind of giving you an idea of scale of like the equivalent of one computer basically on the cluster compared to a regular MacBook. That's just how many more resources are jam-packed in there that you can use to do your research. So why people are using HPC versus, running them on their personal laptops and things the way that, you probably have been used to doing is there's a few reasons why. One of them is size. There are many things that, for example, if you're working on really large data sets, for example, and you're working with a storage that is going to be, you either have, excuse me, when you are working with very large data sets, or when you are doing a lot of processing and analysis on a data set that then generates lots of files that take up lots of space, you likely don't have space for that on your computer. The other one is speed. Problems that take months on a laptop might only take a few hours on a supercomputer, and the reason for that is because of this, because you see the scale of just how much more powerful each of the nodes on a cluster is compared to a regular laptop. The other reason is amount. There are many fields of research that require certain programs or scripts to be run thousands or tens of thousands of times or iteratively, or if you have something that needs to change a single variable and do that every single time for 10,000 different variables. Those are all going to be really, really challenging to get done in an efficient way on a laptop. So the speed comparison that we generally have is when you're driving versus when you're flying. If you're driving 45 miles an hour versus if you're flying 600 miles an hour. Can you drive cross country? Sure, you can, but it's probably a lot easier to take a 7-hour flight from here to the West Coast. So the FASRC, so everything that we've been talking about so far has been really generic. So this is true of basically all clusters in terms of how they're generally set up. And so now we're going to be talking a little bit more specifically about our cluster. So there are also many clusters at Harvard. There's one at the business school, there's one at the medical school, there's a couple of others in different places as well. We are talking specifically about the FASRC clusters. So we work primarily out of 2 data centers. One is MGH-PCC, which is the Massachusetts Green HPC Center. It's located in Holyoke, Massachusetts, which is about 100 miles west of Boston. And this is where the bulk of all of our things are. This is where the literal cluster is. So what you see here in the right-hand side with these cool starry stickers on there that says Canon, what you see there, those are actually the racks that have all of our compute nodes. And there are many such rows of all of these. The other data center that we have is located in downtown Boston. It's called the Markley Center. And for those of you who already have accounts and have probably been getting our emails, that's actually where we had our downtime maintenance for the last few days and where we'll be having our upcoming maintenance next week as well. So that's why whenever you get our maintenance emails, read them because they have information about when things will not be accessible or when jobs might be canceled or when other things like, for example, your lab storage that you might not be able to get to. Now, we have 2 primary clusters, Canon and FASSE. Most of the stuff that we're talking about today is going to be about Canon. Most of it is applicable to FASSE as well, but not quite everything. And the primary difference between these 2 clusters is security level. So Canon is for only level 1 and level 2 data. FASSE is for anything that is sensitive. And when we're talking about these like data level classifications, this is actually the Harvard definition. So if you go to like the Harvard IT security website, this is how they describe all of the different levels of security in terms of how computers and data sets and all these kinds of information get classified. So anything that is like, public information, for example, that's going to be like level 1. Stuff that might be like a little bit like, oh, this is like the work that our lab is doing, but it's, publicly available genomic data, for example. That's also public, so you don't have to worry about that. If you are getting data from a provider that requires you to sign a contract about its use, about its storage, or anything else, if you are working with data that you are generating, like for example, if you're doing brain image scanning, or if you are working with animals, things of that sort, anything that is sensitive, that has a DUA, a DAT, an IRB, you have to first go through the Harvard system in order to get those signed off there. And after that, before you start either uploading your data to the cluster or before you start doing any analysis, anything of that sort, we have to know about it too. Because many people who sign up through the Harvard IRB system, sometimes they do those experiments on like computers in their lab. They don't actually use a cluster for it. So we don't see every single thing that comes in. We need to know all of the different information about your project, and we talk to you and your PI to figure out the best kind of storage, whether or not we're able to legally comply with all of the DUA provider contracts, all of those things. And it is upon you and your PI to know your data, to know what is sensitive and what isn't. And if there is anything, and so there are many times where if you are working with a private entity, such as a corporation or a company, it might not necessarily be sensitive data in terms of personally identifiable, but that company might want their data to be treated as such. So even in those cases, we still need to know about it to know what types of security we need to, what we need to do to ensure that we can be in compliance with such requests when hosting those data sets on any of our clusters. So definitely a lot of paperwork involved and a lot of red tape on the Harvard side. And so once we get all those things done, then only can we say, feel like here is a space that you have, you can upload your data here. This is a cluster that you can use to do your research, and you can go from there. So this is a graphic about what it looks like anytime that you're connecting to the cluster. Now, if we're sitting here and we want to connect to the cluster, we're generally going to do so in one of two ways. We're either going to log into a login node or we're going to log into Open On Demand. So Open On Demand goes by a couple of different acronyms. It's called OOD, which stands for Open On Demand. It's called VDI, which stands for Virtual Desktop Interface. All of those are the same thing. The primary difference between these two is a login node. Whenever you log into one, you're using a terminal or a command line. And Open On Demand is going to be graphical. It's going to be something that you open up in a browser and you're using your mouse to like move around and click and enter stuff. So that's your main entry point to the cluster. From there, you can see that these are connected to everything. Both of these are connected to all of our file servers. So that's going to be your home directory. It's going to be all of your lab shares. It's going to be all of the places where you're keeping your data. And it's also going to be connected to the cluster, which is all of the compute nodes. Global Scratch here, we'll get into that into a second. It's a type of fancy storage that we use just for jobs. The important things to know about these entry points, particularly for login nodes, is that login nodes are small shared resources. They're not intended for a lot of computation. They're basically just like a jumping point. If you think about whenever you enter a doctor's office, you're like in a lobby first, and then you go into like an examination room afterwards. The lobby is like where you can do things like you fill out your paperwork or you do like, a few light things. Login nodes are the same way. They're the place where you can start jobs. It's where you can keep track of your jobs if you already have something running. You can move files around. You can be editing stuff, things like that. But as soon as you want to actually do something, if you want to be running a MATLAB job or if you're trying to debug your Stata code, things like that, you have to start a job, which then connects to the cluster. So that's where you can do like the bigger, heavier thing. So looking at what these things look like in real life. So the compute nodes, or these racks, you can see here, this is what it physically looks like. So here we have each one of these like rack units is a compute node. And that's why they're so beefy, because they have a couple of CPUs with that many processors and that much memory. So they take up a lot of space and they're really heavy. What we have here up at the top with all of the blue cabling is something called an InfiniBand switch. InfiniBand, which is the same like blue connection that we can see here, is a special type of networking fiber. So what that means is there are many ways to connect devices to one another. For example, Wi-Fi. When I'm connecting my computer to Wi-Fi, I don't need any wires that are plugged into my computer in order to access it. And Wi-Fi is great, it can be fast. But if I have a wired connection, it's going to be many, many times faster. So for these wired connections, there are different levels. In this case, what InfiniBand does, it's not about connecting to the internet, it's just about connecting these nodes to one another. And what that does is that it reduces latency and lag in communication between these different nodes. So InfiniBand is like one of the best types of network connections you can get at the moment on the market. And what this does is that we have connected all of our compute nodes to each other and to Scratch and to some of our other storages using this. So what that means is that within that one data center, all the stuff that is connected can talk to each other really, really fast. There isn't going to be that same kind of lag as there would be if we were using something that was a little bit more commercial grade. Now, this is a little bit of the architecture of a node. So a node is basically like a computer. So in a computer, you have a bunch of different components. And so here, like in a laptop, for example, you have some additional interfaces like a screen and a keyboard and things like that. We're basically just looking at the guts right now. So here, this one is similar. So from Lenovo, these are the same types of servers and stuff that we actually have in the data center. So you can see here that this picture is actually two nodes. So it's the same thing mirrored on both sides. And this is the different components in each part of it. So each CPU, which is like a brain, is going to be here. And then you have RAM, which is random access memory, or just commonly called memory, which are all these little green chips. And those are the main important parts that we care about at the moment. We actually have water-cooled nodes in our primary data center, which is MGHPCC. And the reason why this is really fancy and really cool and also really important is because we run millions of jobs on the cluster every single year. On any given day, we are churning through thousands of jobs of all different kinds. Like many are very small jobs, some of them are really big and take a very long time, and all of that. And as most of you probably know, when you use a computer for a long time or it's doing a lot of stuff, it tends to heat up. And when it tends to heat up, then it gets really slow. So we invested in water-cooled nodes, which is there are a bunch of tubes that have chilled water running through them, and these nodes are built such that they have like different channels for these cooled water to go through, and that brings down the temperature of the nodes, which means that these nodes can keep running longer and faster to continue doing more computation, because otherwise when they heat up, then you have to wait for them to cool down and it reduces the life and all of that. So like, yep, a node is a computer in the cluster. A CPU stands for a central processing unit or a processor, has many cores. Each core runs a basic unit of compute, or a core is a basic unit of compute, and it runs a single instruction of code. So anytime that you are coding something, for example, in Python, or if you're opening something like Firefox, what your computer does is that it interprets each one of those actions and converts it into really, really low-level language and makes it such that each little core has one small job to do so that all of these cores can run at the same time and do the thing. Now, the reason why we're talking about all of this, or like why this is important in the first place, is because when you're working on a laptop and it's just you don't have to really think much about the resources that you're using. You probably have an idea that if you are running like, 100 tabs at a given time, that your computer's going to slow down, but that's fine because it's you, right? So you can close the things that you no longer need. You can let the things that you want to have running, you can keep those there. But clusters are, by definition, shared resources, which means that you are sharing this with lots of other people. We have about 800 lab groups that currently use the cluster. And everyone comes from different fields, so everyone is using the cluster in like really, really different ways, which means that everyone also has different needs. The reason why we have to go through all of this is because you need to know what to request whenever you're going to run a job. And a job is basically your request to use a certain amount of resources on the cluster for a specific amount of time. Whenever you're doing coding on your computer, you don't have to think about, oh, okay, how long am I going to be using like my MATLAB window for, and like what's it going to be doing on my computer? You don't have to consider those things, but on a cluster you do, because you have to request those ahead of time, which gets into job scheduling. So because the cluster is multi-tenant, how do we ensure that everyone gets a chance to use it and use it fairly? And the answer to that is we have a scheduler. Our scheduler is called Slurm, which is the simple Linux utility for resource management. And Slurm's job is to manage the entire job queue for absolutely everyone. It provides you the status of all of your jobs. It determines the order in which jobs are executed and on which nodes those go on. It also handles the priority for them, and it also handles the queues. So it does a lot of things. Slurm is also very powerful, has a lot of different options and flags, and Slurm is also not something that we developed. It is a very popular tool in use across many clusters, which the great thing about that means that it also has a lot of documentation online as well. We also have documentation on our website about this, but Slurm is also really easy to look up for different types of things that you might be looking to do. So, job management philosophy. How does a job scheduler work? So the idea behind the way in which we have optimized Slurm is we want to maximize the cluster usage. The cluster is not really of much use if it's just like sitting around waiting for like perfectly sized jobs to fill it. So we actually have backfill. So what this does is that here in this picture you can see with these nodes, time is this way, and these are a number of nodes. Job C is a really big job. It doesn't necessarily require like the full amount of time, but it does require a lot of nodes, which means all of those nodes have to be available at the same time for job C to run. So what the scheduler does is that it says, okay, job A and job B, I can schedule both of those at the same time and also still have more room to schedule other smaller jobs that might fill in while waiting to get these resources available for job C. And job priority is also important. We don't do first come, first serve. Priority depends on your group's score on the cluster and as well as how long your job has been waiting in the queue. Like from the time that you have submitted your job, it's then pending until when it gets to start running. The longer it's pending, then the higher in priority it goes. Jobs with higher priority get scheduled ahead of jobs with lower priority. So the way in which the cluster looks at these high versus low priority jobs is that it does all of the high priority jobs first, and then in all of the little gaps in between, it backfills them with all of the low priority jobs. That way, even all of these jobs that are low priority and small, they don't have to wait for all of these jobs to complete just to get their thing to run. They might still have to wait a little bit, but for the most part, when they're smaller or if they have lower priority, there generally is enough space for them to run somewhere within a reasonable amount of time. So choosing computational resources can be challenging, especially if you haven't done it before. How do we choose things like memory and cores and partitions and file systems? And especially if this is your first time running on the cluster, there's going to be a lot of trial and error. It's going to be a lot of trying things out, comparing notes with your lab mates. Your lab mates, especially if they have experience on the cluster, will be a great resource for you to use, as they will be able to tell you a lot of things that work specifically for their type of workflow. And that's all really important because even if you have a job that runs really perfectly on your laptop, let's say it takes a week to run, don't try and start running that week-long job on the cluster right away. Start with a really, really small test case, like an hour. Make sure that your software is working in the way that you expect. Make sure your results are also what you expect. Then increase slowly the amount of data that you're processing or the amount of time that you're requesting or the amount of cores that you're requesting, and see how your job efficiency scales. That way you'll have a good idea. Is your job resource, are those job resources being scaled linearly? Is it more like this? Is it more like this? You need to know what kinds of resources to request before you do a production run, because then you might end up requesting a job that's going to take a week to run, but you might need to wait several days before that job even starts. And then after that week is over, you might realize that your job didn't actually execute in the way that you had hoped, and now you've already lost a week and a half. So if you start small and you scale up, then you will be using your own resources more efficiently, as well as those of your group, and also you will be saving a lot of time on your end. So these are the different partitions that we have for you to be running your jobs on. For Slurm, we have all of our different compute nodes that are partitioned into different ways based on different identifying factors, essentially. And what we have listed here is basically just the stuff that is public access to absolutely everyone on the cluster. Many of you might have PIs that have already put in their own money to lease their own private partition. There are ways to find out what exactly it is that you have access to. So you have access to those and this as well. This is for everyone. So on Canon, the names of these partitions are like Sapphire, Share, GPU, Test, all of these different things. And they have different limitations on them. So for example, the test partition. The time limit on here is 12 hours. So if you have a job, so if you're trying to work on debugging your code or you're just getting started on the cluster, the test partition is a good place to start. You can only request up to 12 hours on here. There's a lot of memory on here for each node, along with 112 cores per node. And the idea behind the test partition is that you shouldn't really have to ever wait to get a session started on there. That's why we keep the time limit so small. And there's also a limit on the number of jobs that one person can submit to that partition at a time, just so that there's a lot of through traffic, and that way you don't actually have to ever wait just to get something going for debugging or getting started. GPU test, it's the same deal, except GPU test is only for GPUs. If you see something in here that doesn't have the name GPU in there, it doesn't have GPUs, it's only CPUs. And if you don't work with GPUs, then you don't have to worry about it. You can just submit to any of the CPU partitions. So When you start running on the test partition, and then you start having a better idea of the kinds of resources that you need, all of that, and now you're ready to do a production run, now you can choose one of the larger partitions. For example, Sapphire, Shared, these both have a time limit of 3 days. You can see here that the shared partition is considerably bigger, but Sapphire has more memory per node. If you are also working on your own, like testing purposes, for example, but you need additional memory or you need additional time, it's fine to request jobs on other partitions, even if you are just testing. That there's no really restriction on the kinds of work that you can do on any one of the partitions, with the sole exception being that if you're running on a GPU partition, you have to request a GPU regardless of whether or not you use it, but you have to request a GPU. Otherwise, your job submission will come back and say, error, like, you did not request a job properly. So we also have a couple of other partitions like big mem and intermediate. Intermediate has a much longer time allocation. Like you can request a job anywhere from 3 to 14 days. Big mem is because it has much more memory. Big mem intermediate, more time and more memory. Unrestricted, no limit on the time, but only 184 gigabytes of memory per node. So a lot of the jobs and stuff that are in unrestricted need to run for longer than 2 weeks. If your PI owns anything, all of these things will be different. Slurm can tell you more about that in terms of what you're able to request. And there are 2 partitions in particular that behave differently, and those are called the requeue partitions. So we have a GPU requeue and we have a serial requeue. Serial requeue is for CPUs, GPU requeue is for GPUs. Time limit's the same for 3 days. What these requeue partitions do is basically, if we pretend that, or here, the requeue partitions work such that if I am a member, if my PI has purchased or leased some hardware and we have our own personal partition, and right now no one in my lab is running any jobs at all. So that hardware is just sitting there idle, like absolutely nothing's running on it. And you have a job that you want to run, and you submit a job to the serial requeue partition. The serial requeue looks to see at idle hardware that might be PI owned, and it looks to see that and says, hey, no one's using this resource right now. So it takes your job and it puts it on my PI's hardware because right now no one's using it, and it lets it run and do all of that. Let's say while your job is running, I log in and I'm like, I want to do some of my calculations and all of that. So I log in and I submit a job. Because it's my PI, I have priority over you because I'm part of the group that has exclusive access to this. So what happens is your job gets kicked off and starts again somewhere else, wherever there happens to be space. Because I have the priority on there, then I'm the one that gets to use that hardware when I log in and I start using it. If no one happens to be using it, then rather than letting that hardware go to waste, we let anyone submit jobs to the serial requeue partition, and Slurm figures out where exactly all of those jobs can fit in. So the thing about the serial requeue partition is that your job might, be up to 50% or something like that complete before it needs to stop and then gets requeued elsewhere. So then it starts again from the beginning. So we don't recommend jobs that are really complex be on here, or jobs that can't really handle that kind of interruption, especially if you're like appending output to like a file, because then you need to know when one run completed and the second one started. The requeue partitions are the only partitions in which you have to worry about your job getting stopped and started somewhere else. None of the other partitions do that. The nice thing about these requeue partitions is that they charge really low fair share, which we'll get into in a second. So that makes it really convenient if you have a lab that does a lot of computation and always has really low scores in the cluster and it takes forever for your jobs to start. The requeue partitions are a really great way of still being able to get your jobs running. But your code also has to have some degree of resiliency, or you have to be able to account for that by creating checkpoints in your code, for example. Now on FASSE, which is the secure cluster, basically everything is same concept, just different name and different parameters. So there's still a test partition here. There is a serial requeue partition here. but you can see here that the time limit on FASSE is 7 days versus the 3 days on Canon. The FASSE is like the FASSE partition is the equivalent of like the shared partition. It's like the main partition where everyone does like all of their production work. The FASSE GPU has the GPUs in there. The big mem has almost 500 gig. The ultra mem has 2000. Remote viz is specifically for remote visualization, but also only one node. You can also see here that based on these node counts, FASSE is considerably smaller than Canon. But at the moment, it does happen to meet all of the needs for our current FASSE members. And again, for your PI-owned hardware, it depends. Some PIs have some on FASSE, some have them on Canon, some have them on both. And note that you can't cross streams. If you are currently on FASSE and you're trying to run some computation on there, and you notice that the queue that you're trying to run in is really busy and that Canon's not very busy, you can't run your FASSE jobs on Canon, and you can't do it the other way around either. You have to keep things in their stream for security purposes. Anything that's on Canon stays on Canon. Anything that's on FASSE stays on FASSE. Now, if you're trying to figure out, well, does my PI have any of this? Maybe your lab documentation is up to date. If not, then perhaps you will be inspired to update it yourself. And if not, you can always see what partitions you have access to with commands for Slurm. So all of these commands that are Slurm commands in particular usually start with a letter S. So for here, SPart stands for Slurm partition. And so this shows these are all publicly owned queues. So as in the ones that we just saw in the chart now. So for SPart, we can see here, these are all the queues that you have access to submit a job to. We can see here that all of these partitions are up, except for this specific one, which is draining, which means that you can't submit a job right now to it. And it also shows you some of the information like the time limits, the node, and the average memory. So this is like a really quick way of seeing what are the names of the partitions you can submit to and some of the information about it. And there are ways to see more specific or detailed information about each of those partitions if you want as well. We also have a lot of these convenient Slurm commands that are on our website that tell you all different types of things if you need to see the status of the nodes on a partition, or if you need to see which accounts you can submit a job under for certain partitions. Those are all, or information about your jobs, all of that. Now, talking about storage. We threw around the word memory a lot earlier when we were looking at the different nodes, and we saw that those are all like the tiny little like green chips basically. But memory and storage are not the same thing. You can think of the difference between memory and storage of when you're driving a car, of the difference between your glove box and the trunk of your car. RAM is basically like the glove box. It's the small amount of memory that you request when you want to run a job because it's whatever you need to have like super handy. And storage, which is where you're having like probably the bulk of all your stuff, is the stuff in the trunk, which is a little bit further away, relatively speaking. Now, you always have access to both, but you also do need to understand the distinction between the two. So this is specifically talking about the different kinds of storage that we have on the cluster. Now again, when you're on your own laptop, you don't really have to think about that. You just have different folders, but everything is stored just on your computer. Everything acts the same, everything looks the same. But that is not the case for cluster computing. As I mentioned before, we have two different data centers. One is in Boston, and the other one is 100 miles away in Holyoke. We have storage in both of them. And everything is connected. You can always access everything. But you have to know the ways in which those storages work to figure out the most efficient way of being able to utilize what you have available. So if you are running jobs, you are automatically going to have a home directory. Home directories are private. They are just meant for you. They're on the smaller side. They're only 100 gigabytes, and these are actually backed up. So it's a really small, safe place for you on the cluster. And this is generally not typical of most of the other spaces that we have. Now, 100 gigabytes and something that you can't really use for collaboration, that's not how, most labs work. Most labs will have different kinds of data sets that might be on the order of terabytes, or you have different folders that you want to be working with your lab mates on, things like that. So for that, we have a lab directory. These are going to be stored in a place called Holy Labs. So anything that is prefixed with the word holy stands for Holyoke, which indicates that data center. All PIs automatically are given 4 terabytes on Holy Labs. This is not backed up, and this is also not expandable. So once you hit that 4 terabytes, you either have to do some cleanup or you have to purchase additional storage because we can't really expand it. We also can't expand home directories either. Also, the important thing is that home directories are located in Boston, whereas all the other storage that we're going to be talking about typically is going to be in Holyoke, which is next to the compute nodes. So you've got your home directory, you've got your basic lab space, which is the Holy Labs or the lab directory. If the 4 terabytes is not enough, then many PIs choose to purchase additional storage, which is called tier storage. There's different tiers. Some of them are backed up, some of them are not. Some of them you can compute against, some of them you can't. Lots of different things. And also that costs like actual like dollar money, like that you put in an expense code for and all of that. Now, when you want to run a job, your home directory is only 100 gigabytes, and it's in Boston, so it's the wrong data center for computing against. So whenever you run a job, you actually want to be running a job from the same data center as the compute nodes because it's physically right next to it, and you want to do so on a file system that is specifically engineered for that kind of intense usage. So whenever you are running a job, you've got your code, you've got your data set, and what happens is that every single line of code every single line of code that is being interpreted, it goes and it does a thing, right? So let's say you read a line, you're going through your data set and you're like looking at a specific entry, and then you output something, and then your code goes back to look at your script and it does another thing and it goes back to your file. So all of this back and forth is essentially called IO, or input output. When we have thousands of people running thousands of jobs, that's a lot of IO. We have specific file systems that are created for this, which is they are suited for high IO. Because if we are going to be having this many people run on like storage that is not really built for that, then it very quickly becomes very slow for anyone to access because there's too much traffic going in. And when people are opening the same files again and again, then those files can also get locked up too. So we always recommend that whenever you're running a job, that you do so on something called Scratch. If you have been using the cluster for a while, you'll know that we used to have something called Holy Scratch. Holy Scratch is going away. We have a new system. It's very shiny and fancy and fast, and it's called NetScratch. On NetScratch, every group has 50 terabytes of space. And the reason why we call it Scratch is because it's a very temporary space. It's really meant for like live active jobs that are running that need additional space for intermediary files. Because you might be running a script, you create a lot of files, and then you're processing your results so that you can actually get, this much that you actually care about, whereas you might have this many intermediary files. That's why we have 50 terabytes per group. But once your files have been there for 90 days, they automatically get deleted. So nothing on here is backed up. If your files have been there for 90 days, they will disappear. So your job is to ensure that any results or anything that's important, that you're not keeping your only copy on Scratch. You've got an entire data storage workflow of what this looks like. So this is just more information about all the different kinds of storage. And this is generally what we recommend for the workflow, for what you store in your home or your lab directory, what you store into your lab storage, what you put into Scratch. So generally, scripts, software, things like that can go into your home or your lab directory. You make a copy in Scratch. It might be that your analyzed data all goes back to lab storage after doing all your computation on the cluster. Now here, when we're looking back to the same graphic that we saw earlier, this global Scratch, you can see is connected by InfiniBand to all of the compute nodes, which means it is really, really fast. Your home directory or like some of the older storage, things like that, will never have, can't even compare to the amount of performance that you will get from running your jobs on global Scratch versus like your home directory. Now, there's something also called local Scratch. Local Scratch is physically located on each compute node, and it's on a little bit on the smaller side. It also depends on the node, so it's about 70 gigabytes per node. And it only lasts for the duration of your job. So let's say you have a 2-hour job, that only gets whatever information you utilize local scratch for, is going to be only there for the duration of your job, because as soon as your job ends, it gets deleted. So this is just physically what the local scratch looks like on your node. You're not required to use this. Uh, if you're going to be using a scratch space, definitely learn how to use global scratch, which is the net scratch, or network scratch, which just means that you can access it everywhere, whereas local scratch is only on that physical node. So here is the slide about data management. So now that you kind of have this idea of like, okay, home is really small and for really valuable things like small code. Global Scratch is really temporary. You can have your input data, your output results. You can do all of that on Scratch. And once you are done running your jobs, then you can take all your results, put them into lab storage. If you don't already use version control, especially for your code, you should start. Git is a very popular one. Code is really important. Most of the times, when you're trying to figure out what exactly is reproducible, code is one of the most difficult things to reproduce. Generally speaking, if you have your raw data and if you have your code, you can always process or like reanalyze all the stuff that you need to in between, but those are the most important things. So everything else might be intermediary as long as you have the raw data, the code, and the final results. So learning how to manage your data storage workflow is really important, because when we don't, that's how we land into a bunch of problems like, oh, we have a bunch of folks who left our lab, but now no one can write to our lab space because it's completely full and no one knows what it's full of. No one knows if any of this information is important or needs to be kept, or if it's part of results that are going to be published or what have you. So it's really important to be talking to your lab mates about what your lab process is, and if you don't have one, to perhaps start on that, because all of these things are shared resources, generally speaking. Only your home directory is just for you. Everything else you're sharing with your lab mates. Your quotas for Global Scratch are shared with your lab mates. Your quotas for lab storage are shared with your lab mates. It's not that person one gets this percentage of the lab storage and this other person gets another percentage. Our storage doesn't work that way. It's this group gets this much, and then how you all choose to use it afterwards is completely on you. So that requires a lot of good communication and also good planning. If you know that someone is going to be working on something that requires, 3 terabytes of space, and you only have 5 terabytes left in your lab storage, well, then you need to discuss whether additional storage needs to be purchased, or if you all need to fix your timelines for who's going to be working on what project based on your ingest expectations for what you need for both datasets, processing, and result space. We're coming up on time. A few last things in general is don't run things on the login nodes. If you try, you will get kicked out. Just you log into a login node, you request a job. Be as accurate as you can. We have a limit of 10,000 jobs per user, and when you're requesting jobs, try to do it for at least 10 minutes. And don't be overwhelming the scheduler by like many, many times a second, like, inputting the same commands and things like that. These are all things that can break the cluster. Not very easily, but when it happens, then it does slow things down for everyone. Being aware of what partitions and stuff that you're going to be using. We definitely recommend that you keep at most 1,000 files per folder or directory, because when you have generally file systems start to take longer time to process a directory if you have more than that. Please don't mine digital currency or misuse Harvard resources like the cluster. And if you have jobs that are poorly behaved or that are doing things that are illegal, such as mining digital currency, or if you are scraping, those are all things that you have to be aware of. Those are jobs that we will kill and can lead to a ban from the cluster as well. If you do use the cluster, we ask that you put us into your part of your publication attributions. And if you need additional detailed information about the specific hardware that we are using or things of that sort, we are happy to help you with that. And As a quick note, like has been a really broad overview of essentially high performance computing at like a 10,000-foot level, but we didn't really get into, oh, okay, how is it that I log in and like I submit a job through a login node or through Open on Demand? And the reason why we didn't do that today is both time, as well as the fact that we actually have specialized training classes for both of those things. And I believe the next one is going to be next week or tomorrow. We have a training calendar that I recommend you take a look at to see the other classes that we have. The classes that we have coming up this month, tomorrow we have the Open on Demand and the CLI classes, which will actually walk you through logging in, submitting a job, what that looks like all these things that we talked about in terms of partition and time and memory and all of that, like how do you request those things? Those classes will actually get into that in detail. We also collaborate with some other groups like Informatics. So there's a Python intensive workshop that they'll be working on. We have got a GPU computing class coming up soon as well as installing software, Python basics, and recommendations for managing research data coming up in March as well. We do tend to update these. These also come out in our maintenance emails as well. Definitely recommend that you take a look at those. We also have lots and lots of things on our documentation website, which is our docs page. You can search things there as well. And we ask that everyone fill out the evaluation. It helps us make these classes better and also be able to serve you, because that is what we are here for. We are here to help all of you to get your work done. So thank you very much for listening to me for an hour. And thank you, Paula, for handling all of the things in chat.